Let R be the relation on set of integers Z defined by R is equal to A comma B such that A and B belongs to Z integers and mod of A minus B is less than or equals to 5. And the difference between any two numbers is always lesser than or equals to 5. And we need to check that this relation is reflexive, symmetric and transitive. And we know that the relation is said to be reflexive if for every A belongs to A comma A must belongs to the relation R. For every element in the set, if A comma A belongs to the relation, then we can say the relation is reflexive. And coming to the symmetric, if A comma B belongs to R, then B comma A belongs to R for A comma B belongs to the set A. If A is related to B, then B is also related to A, then we can say that the relation is symmetric. And coming to the transitive, if A is related to B and B is related to C, if these both ordered pairs are there in the relation, then there must be A comma C belongs to the relation R. Then we can consider that the relation is transitive. So let us check here for this relation R is equal to, it is given ordered pairs A comma B, we can write A comma B belongs to R where mod A minus B is less than or equals to 5. And for reflexive, we can say that for every integer, for every A belongs to Z, A minus A, that is mod, even if you apply mod, it is 0, which always lesser than or equals to 5. So we can consider that for every A belongs to Z, for every A belongs to Z, A comma A, we can say that A comma A belongs to the relation. For every A belongs to Z, A comma A belongs to the relation R, and hence we can say the relation is reflexive. So we can say R is, therefore, relation R is reflexive. And coming to symmetric, let us consider, let A comma B belongs to the relation. So which implies that if an ordered pair is belonging to the relation, then it must satisfy mod of A minus B is less than or equals to 5. And we know that mod of A minus B or mod of B minus C will give the same result because the modulus is applied. So mod of B minus C is less than or equals to 5. So here the elements are interchanged here B minus A. We can also say that B comma A, an ordered pair must belongs to R. So for A comma B belongs to R, we got B comma A belongs to R, and hence we can say that this relation is R is symmetric. So we got the second one, R is symmetric. And coming to the third one we'll consider an example for R is transitive or not. Let us consider an example. Let 1 comma 3 belongs to R, since 1 minus 3 mod, that is negative 2 or 2, modulus of negative 2 is 2, which is less than or equals to 5, and 3 comma, so we can consider 3 comma 8 and one more ordered pair 3 comma 8 belongs to R, which implies mod of 3 minus 8 is negative 5, mod of negative 5 is 5, less than or equals to 5, which is also true. So 1 comma 3 is satisfying the relation and 3 comma 8 is also satisfying the relation. But 1 minus 8, if we can see, which is modulus of negative 7, that is mod 7, modulus of negative 7, 7 which is not less than or equals to which is greater than 5. So we can say that 1 comma 8, here 1 comma 8 does not belongs to the relation. So for a comma b belongs to R and for b comma c belongs to R, but a comma c, this 1 and 8 does not belongs to R. 1 comma 8 is not belonging to the relation, and with this example we can say R is not transitive. So to disprove it, we need to give at least one example. So here one example is enough to show that this relation is not transitive. In general cases, we will prove it, but in the case of not correct, we need to give a counter example.